You're staring at your telescope screen when the alert flashes red. July 1st, 2025. 3 I/Atlas, an interstellar visitor carrying 8 times more carbon dioxide than water, just crossed into our solar system. Its trajectory, a surgical precision course toward Mars. The timing impossible. Just weeks after NASA announced the strongest evidence yet of ancient Martian life hidden in leopard-spotted rocks at Jezero Crater. This cosmic messenger arrives carrying exactly what a dead planet needs to breathe, again greenhouse gases. This isn't random. The mathematical probability of this timing makes winning the lottery look like a certainty, while Earth's telescopes lose sight of it behind the sun. 3 I/Atlas creeps within 30 million kilometers of Mars, invisible, unstoppable, perfectly timed. 3 interstellar objects in 8 years. 3 different chemistries. 1 emerging pattern that astronomers whisper about but won't say out loud. Tonight, you'll witness the invisible encounter happening right now above our heads. You'll understand why this timing shatters everything we thought we knew about cosmic coincidence. Because what 3 I/Atlas is doing in Mars's orbit might be the most significant astronomical event in human history, and we're watching it unfold in real time. If you're the kind of person who needs to know what happens next, who can't sleep when the universe drops mysteries like this, then you'll want to catch every update I bring you. Hit that subscribe button and turn on notifications, but only if this story genuinely excites you. And drop a comment below. Where are you watching from? And what's your theory about 3 I/Atlas? Now, let's dim those lights and dive deep into the cosmic unknown. The encounter is already underway. Right now, as you're hearing these words, 3 I/Atlas is executing a gravitational dance with Mars that began 300,000 years ago, when it departed from a stellar neighborhood we can't even identify yet. Think about that for a moment. This object started its journey before modern humans walked out of Africa, and it's arriving at Mars within the same month we discovered potential life signatures there. If you flipped a coin and got heads 50 times in a row, statisticians would investigate you for fraud. This timing is exponentially more unlikely. Let me paint you the picture of what invisible actually means in astronomy. When you hear that 3 I/Atlas is hiding behind the sun, you might imagine it peeking around like a shy child. The reality is far more dramatic. From Earth's perspective, any object within about 45 degrees of the sun becomes virtually unobservable. The sun's glare overwhelms even our most powerful telescopes. It's like trying to spot a firefly hovering next to a searchlight pointed directly at your face. And 3 I/Atlas's trajectory, either through cosmic accident or something more deliberate, positions it in this blind spot during its closest approach to Mars. Here's where it gets genuinely strange. Professional astronomers use something called ephemeris data, mathematical predictions of where celestial objects will be at any given time. When researchers at the Minor Planet Center calculated 3 I/Atlas's path in early July 2025, they noticed something that made several people pause mid-coffee sip. The object's perihelion, its closest approach to the Sun, occurs on December 8th, 2025. Standard orbital mechanics, nothing unusual there. But the Mars encounter that happens in mid-November, precisely when observational geometry puts both objects in Earth's solar exclusion zone. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury who specialises in outer solar system objects, noted in a September 2025 interview with Sky and Telescope. The trajectory itself follows perfect Newtonian mechanics. There's nothing anomalous about the orbit. What's statistically interesting is the Mars proximity timing coinciding with reduced observability from Earth-based assets. That's scientists speak for, this is really weird. But I'm not saying aliens because I enjoy having a career. You have to understand the observational challenge we're facing. NASA's Mars Orbiter's MAVEN, Mars Odyssey, Mars Reconnaissance Orbiter. These spacecraft are designed to look down at Mars, not up into deep space. They're planetary scientists, not astronomers. They can detect dust storms and measure atmospheric composition. But tracking a comet 30 million kilometers away isn't in their job description. It would be like asking a doctor to fix your car because they both involve complex systems. Sure, technically possible, but not exactly optimal. The European Space Agency's Mars Express orbiter does have a wider field camera called the Visual Monitoring Camera, originally designed as an engineering instrument to watch the Beagle 2 lander's deployment back in 2003. It's still operational, technically. But here's the thing. It has a resolution of 640 x 480 pixels. Your smartphone camera is vastly superior. Asking it to capture meaningful data on 3i/8 lays would be like trying to read a license plate from an airplane using binoculars from the 1970s. So we're essentially flying blind during the most significant part of this encounter. Ground-based telescopes can't see it. Mars orbiters aren't equipped for it. The James Webb Space Telescope is booked months in advance with observation schedules that make getting a reservation at a Michelin star restaurant look easy. By the time JWST can swing its mirrors toward 3i/8 lays for another look, the comet will be millions of kilometers past Mars, and any immediate interaction effects will already be history. Now, let's talk about what we do know from the observations we managed before 3i/Atlas disappeared into the sun's glare. The spectroscopic data from JWST's July observations revealed that carbon dioxide signature we mentioned, but there's more to that story. When comets outgas, they don't just release molecules randomly. The sublimation patterns how ice transitions directly from solid to gas follow predictable physics based on temperature, composition, and solar radiation intensity. Most comets show water ice sublimation beginning around 3 astronomical units from the Sun, that's about 450 million kilometers, roughly the orbit of the asteroid belt. Carbon dioxide, being more volatile, starts outgassing even farther out, around 5 to 10 AU. What's fascinating about 3i/Atlas is that its CO2 production rate remained remarkably stable across observations taken at different distances. In September, when it was at approximately 2.3 AU, the outgassing rate matched theoretical predictions almost perfectly. Too perfectly, some might say, but that's entering speculation territory. The green glow observations from amateur astronomers in early September added another layer to this mystery. When you see green light from a comet, you're witnessing dicarbon molecule C2 getting excited by solar ultraviolet radiation and emitting that characteristic wavelength. It's the same chemistry that makes certain flames burn green. This isn't unusual for comets. What is unusual is the intensity relative to the CO2 signature. Typically, comets with high carbon dioxide ratios show different colour profiles. 3i/Atlas seems to be breaking the standard comet chemistry playbook. Think about Mars for a moment. Not the Mars of sci-fi movies or Elon Musk's fever dreams, but the actual current Mars. It has an atmospheric pressure of about 600 pascals at its surface. Earth's atmospheric pressure is 101,325 pascals. Mars's atmosphere is 0.6% as thick as ours. Imagine trying to breathe air that's been diluted to less than 1% of normal density. That's not even considering that Mars's atmosphere is 95% carbon dioxide already, but there's just so little of it that the greenhouse effect barely functions. Here's the brutal math. For Mars to warm up enough to support liquid water on its surface, not oceans, just puddles, its atmospheric pressure needs to increase by at least a factor of 10, preferably 20 to 30. That requires adding approximately 2 to 3 trillion tons of carbon dioxide to the Martian atmosphere. For perspective, All human industrial activity since the Industrial Revolution has released about 1.5 trillion tons of CO2 into Earth's atmosphere. We'd need to double our entire civilization's carbon output and dump it all on Mars just to get started. How much carbon dioxide is 3I/Atlas carrying, we don't know exactly. Comets are notoriously difficult to mass estimate because we're essentially weighing dirty snowballs from millions of kilometers away, using only the light they reflect and the gas they emit. But based on its observed brightness, estimated nucleus size of perhaps 1 to 2 kilometers in diameter, and that extraordinary 8:1 CO2 to water ratio, rough calculations suggest somewhere in the range of 10 to 100 billion tons of frozen carbon dioxide. That's nowhere near enough to terraforming Mars, not even close. It's like trying to fill an Olympic swimming pool using a water gun. But here's what keeps me staring at the data at 2 a.m. You don't need to terraform Mars completely to make biological signatures more detectable. You just need to create temporary conditions where chemical processes associated with life can briefly flourish on the surface instead of remaining frozen in subsurface ice. What if the question isn't, is 3I/Atlas going to terraform Mars, but rather, could 3I/Atlas trigger a temporary atmospheric enhancement that makes existing subsurface chemistry briefly observable? That's a radically different proposition, and one that the timing makes uncomfortably relevant. The universe, you see, doesn't care about our narrative preferences. It doesn't arrange astronomical events for dramatic effect, except when it does, and then we're left holding our calculators, running the probability equations over and over, hoping the numbers will make more sense the next time. They never do. And that's exactly why you need to understand what Mars was broadcasting to space before this interstellar visitor decided to drop by for a visit that nobody invited, but everyone's now watching with increasingly nervous fascination. The Perseverance rover doesn't know it's making history. It can't feel excitement when its drill bit penetrates Martian mudstone, can't experience that flutter of anticipation when its spectrometers analyze chemical signatures that might rewrite biology textbooks. It's just a very expensive robot following instructions uploaded from Earth, millions of kilometers away, with a 20-minute communication delay each way. But on July 21st, 2024, Perseverance's abrading tool ground into a rock sample that would make human scientists on Earth lose sleep for entirely different reasons than usual. They named the sample Chiava Falls, after a waterfall in the Grand Canyon. NASA loves its poetic naming conventions, and this one feels appropriate because what Perseverance found might represent the geological equivalent of a cascading revelation. Inside this reddish Martian rock, embedded in the ancient mudstone-like secrets frozen in time, were patterns that made even the most skeptical astrobiologists sit up and pay attention. Leopard spots. That's what they looked like under Perseverance's microscopic imager. Millimeter-scale spots, lighter in colour than the surrounding rock matrix, distributed across the sample's surface in patterns that looked almost, and this is the word that makes scientists nervous, organised. Not random splotches, not mineral staining from simple water percolation. Something that resembled, uncomfortably closely, the biosignatures left by microbial colonies in Earth rocks. Let me take you inside those spots, because the chemistry here is where things get fascinating and frustrating in equal measure. The lighter coloured regions contain minerals called vivianite and greigite. Now, if you're not a geochemist, those names mean nothing to you. But here's why they matter on Earth. These minerals form through specific chemical processes that frequently, though not exclusively, involve biological activity. Vivianite is an iron phosphate mineral. It forms when iron reacts with phosphate in the presence of organic matter undergoing decay. Think of it as a chemical fossil of decomposition. When bacteria die and break down, they release phosphate. If iron is present in the right chemical state, you get vivianite crystals growing in the sediment. The green-blue crystals appear in everything from ancient lake beds to Viking Age cesspits. Life's calling card. Preserved in mineral form. Greygit is even more intriguing. It's an iron sulfide mineral that on Earth is almost always associated with microbial activity, specifically bacteria that metabolize sulfate compounds. These organisms, magnetotactic bacteria, for instance, can create greygite crystals inside their cells as tiny biological magnets for navigation. When the bacteria die, the crystals remain, embedded in the sediment like microscopic compasses pointing toward ancient biological activity. But here's the scientific torture of it all. Both minerals can also form through purely abiotic processes. Geological chemistry without any biology involved. The right temperature, the right pH, the right concentration of dissolved ions. And boom, you get the same minerals that life produces. It's like finding a footprint in the sand and not knowing whether a human made it or whether wind and water erosion just happened to create that exact shape. The pattern looks intentional, but nature is a master of creating intentional-looking accidents. Dr. Amy Williams, a NASA astrobiologist working on the Perseverance mission, told reporters in September 2024, "These are the most interesting samples we've collected so far in terms of potential biosignature characteristics. But I cannot stress enough that interesting does not mean definitive. We need these rocks back in Earth laboratories before we can say anything conclusive." You can practically hear the careful hedging in her words. This is a woman who has built her career on not over-promising, and even she sounds cautiously excited. The leopard spot patterns follow the rock's internal layering. They appear concentrated along what geologists call bedding planes, the horizontal surfaces that represent ancient sediment layers. On Earth, when you see biosignature minerals following bedding planes like this, it usually indicates that microbial mats once lived along those surfaces. Picture a pond with slimy green algae coating the bottom. Now imagine that pond frozen in time for 5 billion years, with the algae replaced by minerals. That's essentially what we might be looking at. Jezero Crater, where Perseverance is conducting this investigation, wasn't always a crater. About 3.7 billion years ago, it was a lake. We know this with extraordinary confidence because the rover's cameras have captured stunning images of the ancient delta formations, fan-shaped sediment deposits where a river once flowed into standing water. You can see the layering in the cliff faces, the exact same geological structures you'd find in Earth's river deltas. The Colorado River Delta, the Nile Delta, the Mississippi Delta Jezero once looked like their Martian cousin, complete with flowing water, sediment deposition, and potentially life. The timeline here is critical. Earth's oldest confirmed fossils date to about 3.5 billion years ago, stromatolites from Western Australia. Layered structures built by bacterial communities in shallow marine environments. Mars's Jezero crater was a functioning lake system around the same time period. Both planets had liquid water. Both had the necessary chemical ingredients for life. Both had energy sources from volcanic activity and solar radiation. The conditions were parallel, but Earth kept its atmosphere and magnetic field. Mars lost both. Earth's life flourished, diversified, and eventually started building podcasts and YouTube channels. Mars's life, if it ever existed, got frozen, desiccated, and irradiated into geological memory. The question isn't whether Mars could have supported life. The chemistry says yes. Absolutely. The question is whether it actually did, and whether any trace of that biological experiment survived long enough to leave detectable signatures in rocks that Perseverance is now grinding samples from. Here's what makes the timing of 3I/Atlas's arrival feel less like coincidence and more like cosmic irony, we announced these leopard spot discoveries to the public in early September 2025. By that time, 3I/Atlas had already been tracked for 2 months and its Mars trajectory was confirmed. The astronomical community knew this interstellar visitor was inbound, but the general public, the people who watch science documentaries and read space news, they learned about both events almost simultaneously. Imagine you're scrolling through your news feed. Headline 1, strongest evidence yet of ancient Martian life discovered in crater rocks. Headline 2, mysterious interstellar comet approaching Mars with unusual chemical composition. Your brain, wired by millions of years of evolution to detect patterns and assign meaning, immediately starts connecting dots. These things must be related. The universe doesn't drop 2 Mars-related bombshells in the same month without reason. Except, maybe it does. Maybe the universe is just that random. Or maybe we're witnessing something that our current scientific frameworks aren't equipped to fully explain yet. The leopard spots contain another chemical signature that NASA's press releases mentioned only briefly, almost as an afterthought: organic molecules. Not life, not even close to life, but organic molecules, carbon-based compounds embedded in the same rock matrix as the Vivianite and Greigite. On Earth, when you find organics, the minerals associated with bacterial activity, and layered sedimentary structures all in the same sample. That's basically a biosignature jackpot. It's not proof, but it's the kind of circumstantial evidence that makes prosecutors confident about conviction. But Mars isn't Earth, and we've been fooled before. In 1996, President Bill Clinton stood in the White House Rose Garden and announced that a Martian meteorite found in Antarctica, ALH 84001, contained potential evidence of ancient Martian life. The rock showed mineral structures that looked like fossilized bacteria, organic molecules, and magnetic crystals similar to those produced by Earth microbes. The scientific community was divided. Some researchers were convinced, others were skeptical. 28 years later, the consensus has shifted toward abiotic explanations for ALH 84001's features. Not definitive science rarely delivers those, but probable. Terrestrial contamination could explain the organics. The fossilized bacteria were likely just mineral structures that happened to look biological under electron microscopes. The magnetic crystals could form geologically. It was a cautionary tale about letting excitement override skepticism, about seeing what we want to see in ambiguous data. That's why NASA scientists are being so careful with Cheava Falls. They've been burned before. The media interpreted their 1996 enthusiasm as certainty, and when the evidence weakened, the public felt deceived. Trust in scientific announcements took years to rebuild. So now, when Amy Williams says interesting but not definitive, she means it. These leopard spots might be biological, they might be geological. The only way to know for certain is to bring the samples back to Earth, where laboratories equipped with instruments that weigh several tons can conduct analyses impossible on Mars. The Mars Sample Return mission is scheduled for the 2030s. Maybe, possibly, if funding continues and nothing goes catastrophically wrong, that means we're looking at potentially 5 to 10 years before anyone can definitively answer whether Cheava Falls represents ancient Martian biology or just really compelling geology. A decade of uncertainty. A decade of arguments. A decade of headlines flip-flopping between Mars had life and Mars probably didn't have life. And into this scientific soap opera, right on schedule like a plot device in a screenplay nobody remembers writing, arrives 3I/Atlas, carrying the exact chemical ingredient Mars would need to wake up its dormant atmospheric chemistry, even temporarily. Have you ever experienced a moment where the coincidences pile up so high that you start questioning whether coincidence is even the right word anymore, where the universe seems to be winking at you, daring you to connect dots that reason says shouldn't connect. That's where we are right now, staring at leopard spots in Martian mudstone while an interstellar messenger closes in on the same planet, both events occupying the same historical moment, separated by millions of kilometers but connected by timing that statisticians can't explain. The rocks aren't talking yet. They won't. Not until we bring them home. But the universe seems to be having a conversation with us anyway, and the words are written in carbon dioxide trails and mineral patterns, in hyperbolic trajectories and ancient lake deltas. Whether we're reading the message correctly or just seeing patterns in cosmic static, well, that depends entirely on what happens when 3I/Atlas completes its invisible encounter and Mars's atmospheric sensors start recording data that nobody has thought to check yet. 3 interstellar visitors in 8 years. If you think that's normal, let me give you some perspective that'll change your mind. Before 2017, humanity had never confirmed a single object from beyond our solar system passing through our cosmic neighborhood. 0. Not 1. We theorized they existed, the math said they should, but actually seeing one, that was the astronomical equivalent of spotting a unicorn. Then October 19th, 2017 happened. Robert Verick, an astronomer working with the Pan-STARRS telescope in Hawaii, noticed something peculiar in the data. An object moving fast, too fast. Its velocity and trajectory didn't match anything bound to our sun's gravitational influence. After days of verification and increasingly frantic calculations, the astronomical community reached a consensus that made headlines worldwide. We detected our first confirmed interstellar visitor. They named it one as /Oumuamua, Hawaiian for scout or messenger. Oumuamua was bizarre from the start. Its shape elongated like a cigar or perhaps a pancake, depending on which research team you believed reflected light in ways that suggested a 10:1 length-to-width ratio. Nothing in our solar system looks like that. Asteroids are lumpy potatoes. Comets are dirty snowballs. This thing was geometrically weird, and weird in astronomy usually means interesting. But the real strangeness came later. As Oumuamua swung around the sun and headed back toward interstellar space, it accelerated. Not much, just a tiny boost that shouldn't have been there. Objects following pure gravitational trajectories don't speed up unexpectedly. Comets can accelerate through outgassing when solar heating vaporizes ice and creates a natural rocket effect. But Oumuamua showed no visible coma, no gas tail, nothing that indicated active outgassing, yet it was accelerating anyway. Dr. Avi Loeb, chair of Harvard's astronomy department, published a paper suggesting the acceleration could be explained if Oumuamua was artificially constructed, perhaps a light sail propelled by radiation pressure. The media exploded. Harvard scientist says alien spacecraft visited solar system. The scientific community was less enthusiastic. Most astronomers argued that exotic but natural explanations, perhaps hydrogen ice sublimation invisible to telescopes, made more sense than immediately jumping to alien technology. The debate continues today, unresolved and probably unresolvable. Oumuamua is long gone, currently about 4 billion kilometers from Earth and getting farther every second. We'll never catch up to it, never get another look, never definitively answer what it was. It arrived, confused everyone, and left. The ultimate cosmic mystery guest. 2 years later, in August 2019, we got visitor number 2. Crimean amateur astronomer Gennady Borisov spotted it using a homemade 65cm telescope, proving you don't need NASA's budget to make history. This one behaved exactly like astronomers expected an interstellar comet to behave. Visible coma check, Gas and dust tail check. Outgassing matching predictions check. Chemical composition similar to solar system comets check. They named it 2I/Borisov, and frankly, it was boring in the best possible way. It followed all the rules. Its chemistry showed water ice, carbon monoxide, and dust in ratios comparable to comets from our Oort cloud. When it brightened near the sun, the brightness increase matched theoretical models perfectly. Borisov was the control group, the baseline normal that made Oumuamua look even more anomalous by comparison. Astronomers breathed a sigh of relief. Okay, they thought, interstellar objects are a real thing we can now study. Most will be normal, predictable, governed by standard physics and chemistry. Oumuamua was probably just a statistical outlier, the weird cousin that every family has. Nothing to panic about. Then came July 2025. 3I/Atlas appeared, and immediately the pattern, if there is a pattern, became more complicated. Not as bizarre as Oumuamua, not as boringly normal as Borisov, something in between, which might actually be more troubling than either extreme. Here's what keeps me up at night, the chemistry. Oumuamua showed no outgassing. Borisov showed normal comet outgassing dominated by water. 3I/Atlas shows extreme carbon dioxide outgassing with an 8:1 ratio to water. 3 visitors, 3 completely different chemical profiles. That's either remarkable diversity in interstellar object composition, or we're missing something fundamental about what we're observing. Let's talk about what that CO2 dominance actually means. When comets form in the outer regions of star systems, their chemistry reflects the temperature and composition of their birth environment. Water ice dominates in warmer regions. Think Jupiter's orbit and inward. Carbon monoxide and carbon dioxide become more prominent farther out, in the frigid zones beyond Neptune where temperatures drop below 40 Kelvin. A comet with 3I/Atlas's chemistry likely formed in the extremely cold outer reaches of its home star system, perhaps 50 to 100 astronomical units from its parent star for comparison. Neptune orbits 30 AU from our Sun. We're talking about formation zones in the deep freeze, where even carbon monoxide, which vaporizes at incredibly low temperatures, struggles to remain gaseous. What does this tell us? That 3I/Atlas comes from a stellar neighbourhood with conditions radically different from where Borisov formed. 2 interstellar comets, 2 completely different chemical fingerprints, suggesting 2 completely different origin systems. The galaxy isn't making these objects from a standard template. There's wild variation out there. Now consider the timing of discoveries. Oumuamua, October 2017. Borisov, August 2019. 3I/Atlas, July 2025. The gaps are shrinking 22 months between first and second, then 71 months between second and third. We're not discovering them faster because they're arriving more frequently. We're discovering them faster because our detection networks are improving. Pan-STARRS, Atlas, the Vera Rubin Observatory coming online, our ability to spot these fast-moving objects is rapidly increasing. Dr. Matthew Knight, a comet researcher at the US Naval Academy, estimated in a 2020 paper that interstellar objects probably pass through the inner solar system several times per year. We just couldn't see them before. They were always there, invisible ghosts zipping through our neighbourhood at 26 kilometers per second, and we were cosmically blind. Now we're developing the eyes to see them, and suddenly the universe looks far more crowded. But here's the statistical wrinkle that nobody's talking about publicly, but everyone's calculating privately of the 3 interstellar objects we've confirmed. One is approaching Mars during a year when we've discovered the strongest biosignature candidate in Martian exploration history. 1 out of 3, that's a 33% correlation rate, in a sample size of 3. That's essentially meaningless statistically. It could be pure chance, or it could be the beginning of a pattern we don't yet have enough data to recognize. What if interstellar object traffic isn't random? What if there are gravitational highways through the galaxy, routes that objects naturally follow, and Mars happens to sit near one of those cosmic interstate systems? What if planetary systems with certain characteristics like Mars's ancient lake systems and biosignature potential are somehow attracting or influencing these visitors in ways our current physics doesn't account for? I know how that sounds. I can hear the skepticism in your head right now, and honestly, that skepticism is healthy. Science advances through skepticism, through demanding evidence before accepting extraordinary claims. But science also advances through noticing patterns that don't fit current models and asking uncomfortable questions about what those patterns might mean. 3 visitors, 3 chemistries, one approaching a planet that might have once harboured life, arriving precisely when we're discovering evidence of that ancient biology. The numbers are small, the coincidence is large, and somewhere between those 2 facts lies a question that's going to haunt astronomy for years. What happens when we've detected 30 interstellar objects instead of 3, and the pattern either disappears into statistical noise or becomes impossible to ignore? Carbon dioxide gets a bad reputation on Earth. We blame it for rising sea levels, melting glaciers, and increasingly angry hurricanes. Politicians argue about it. Scientists measure it obsessively. Your car produces it. You exhale it with every breath, about 200 milliliters per breath, if you're curious, which means you're personally responsible for roughly 200 kilograms of CO2 emissions per year just from existing. But on Mars, carbon dioxide isn't the villain, it's the potential saviour. Let me explain why this one molecule matters so much to a dead planet trying to remember what warmth feels like. Mars's average surface temperature is minus 63 degrees Celsius. That's minus 81 Fahrenheit for Americans still resisting the metric system. At the equator, on a perfect summer day, temperatures might climb to a balmy 20 degrees Celsius, 68 Fahrenheit. Pleasant t-shirt weather, but that warmth lasts only a few hours before plummeting back to minus 73 Celsius overnight. The temperature swing is 93 degrees in a single day. Imagine if Earth's weather oscillated from Miami beach conditions to Antarctic winter every 24 hours. Your heating bill would be astronomical. Why does Mars experience these insane temperature swings? The answer is atmospheric density, or rather, the lack of it. Earth's thick atmosphere acts like a planetary blanket, trapping heat during the day and preventing it from radiating into space at night. Mars has no such blanket. Its atmosphere is so thin that heat escapes almost instantly. The ground warms up when sunlight hits it, then radiates that warmth directly back into space the moment the sun sets. No buffer, no insulation, just raw, unfiltered heat loss. Now here's where carbon dioxide becomes interesting. CO2 is what scientists call a greenhouse gas. And before your eyes glaze over with climate change fatigue, stay with me because on Mars this property is desperately needed. Greenhouse gases trap infrared radiation heat in the atmosphere. They let sunlight pass through to warm the surface, but then they prevent that heat from immediately escaping back to space. It's a one-way mirror for energy. Light gets in, heat stays trapped. Earth's atmosphere is only 0.04% carbon dioxide. Yet that tiny fraction is responsible for keeping our planet about 33 degrees Celsius, warmer than it would be without any greenhouse effect. Mars's atmosphere is 95% carbon dioxide, so you might think it should be even warmer. Right. Wrong. The total amount of atmosphere matters more than the percentage composition. Mars has so little air that even a 95% CO2 concentration barely moves the temperature needle. It's like trying to warm yourself with a single thread from a blanket instead of the whole blanket. Doctor. Bruce Jakosky, principal investigator for NASA's MAVEN mission, calculated in a 2018 Nature Astronomy paper that Mars would need its atmospheric pressure increased by at least a factor of 50 to create enough greenhouse warming for liquid water to exist on the surface. Not occasionally, not in small pockets, but globally and sustainably. That requires adding approximately 1.5 trillion tons of carbon dioxide to the Martian atmosphere. For context, that's roughly equal to all the CO2 currently locked in Earth's polar ice caps. Where would you get 1.5 trillion tons of CO2 for Mars? The traditional terraforming proposals suggest several sources. You could bombard the polar ice caps with nuclear weapons to vaporize the frozen CO2 trapped there, about 5 trillion tons worth according to estimates. Elon Musk famously suggested this on Twitter, then had to clarify he was only sort of joking. You could import ammonia-rich asteroids from the outer solar system and crash them into Mars, releasing greenhouse gases through impact chemistry. You could build massive orbital mirrors to focus sunlight onto the ice caps, sublimating CO2 through brute force solar heating. All of these proposals share one characteristic: they're fantastically expensive, technologically challenging, and require resources humanity won't possess for decades, possibly centuries. They're science fiction solutions that might become science fact someday, but not anytime soon, not in our lifetimes. But what if the universe delivers CO2 naturally? What if comets, specifically interstellar comets with unusual chemical compositions, serve as nature's atmospheric delivery system? Let's do the math on 3I/Atlas. Its estimated nucleus diameter is somewhere between 1 and 2 kilometers, assuming it's roughly spherical. Comets usually aren't. But we need a starting point that gives a volume of about 0.5 to 4 cubic kilometers. Comet nuclei aren't solid ice. They're more like frozen dirt, with densities around 500 kilograms per cubic meter, roughly half the density of water ice. This puts 3I/Atlas's total mass somewhere in the range of 250 billion to 2 trillion kilograms. Now apply that 8:1 CO2 to water ratio. If the comet is 80% carbon dioxide by mass, and that's a generous interpretation of the spectroscopic data, we're looking at 200 billion to 1.6 trillion kilograms of CO2. Let's split the difference and call it 500 billion kilograms, or 500 million tons of carbon dioxide. That sounds enormous, until you remember Mars needs 1.5 trillion tons for meaningful atmospheric change. 3I/Atlas carries at most 0.03% of what's required. It's like trying to fill your swimming pool using an eyedropper. You're technically adding water, but nobody's going swimming anytime soon. Except, and this is where things get interesting, you don't need to terraform Mars completely to trigger observable atmospheric changes. You just need to create temporary conditions where chemical reactions that normally don't occur can suddenly happen. Think about it this way. Mars's current atmospheric pressure is 600 pascals. Water boils at that pressure at just above 0 degrees Celsius. Liquid water cannot stably exist on Mars's surface right now except in tiny, temporary films that evaporate almost instantly. But if you temporarily increased atmospheric pressure even slightly, say, to 1000 pascals, the boiling point rises to about 7 degrees Celsius. Suddenly liquid water can exist during daytime temperature peaks, at least at equatorial regions. What could 500 million tons of CO2 do if it were added to Mars's atmosphere? Current models suggest it would increase atmospheric pressure by roughly 50 pascals. Not much. Barely detectable. But combined with seasonal CO2 sublimation from Mars's natural ice caps, which adds about 25% to atmospheric pressure during southern hemisphere spring, you could theoretically create localized pressure increases exceeding 100 pascals. Still not enough for stable liquid water, but enough to change chemical reaction rates. Enough to alter how existing subsurface ice interacts with the atmosphere. Enough to potentially make dormant chemical processes temporarily active again, creating signatures that orbital instruments might detect. Dr. Christopher Mackay, a planetary scientist at NASA Ames who's spent 40 years studying Mars habitability, noted in a 2021 interview, Mars isn't dead in the way people think. It's dormant. The chemistry is still there, frozen and waiting. All you need is a trigger temperature, pressure, liquid water for even brief periods, and suddenly you get chemical activity that looks remarkably biological even when it's not. That's the scenario that makes 3 Ice/Atlas's timing so intriguing. Not that it's going to terraform Mars. Not that it's delivering enough CO2 to wake the planet up permanently. But that it might provide enough temporary atmospheric enhancement to trigger chemical processes we could actually observe from orbit, creating a brief window where Mars's subsurface chemistry becomes surface chemistry. And if that temporary enhancement coincides with biosignature investigations at Jezero Crater, where Perseverance is literally grinding rocks looking for signs of ancient biological activity, then we're not just observing a comet fly by, we're potentially watching a natural experiment in planetary chemistry that hasn't occurred in billions of years, happening right when humanity finally has the tools to measure it. Is the universe that conveniently timed? That's not a question chemistry can answer, but it's the question everyone's thinking about while 3 I/Atlas continues its invisible approach, carrying its payload of CO2 toward a planet that's been cold and dry for longer than complex life has existed on Earth. Let's talk about probability, because that's where this story either falls apart into meaningless coincidence or becomes something that demands serious attention. I'm going to walk you through the math, and I promise to keep it as painless as possible. But you need to see these numbers to understand why astronomers are having quiet conversations in observatory hallways that they're not having publicly yet. First, let's establish what we're calculating. What are the odds that an interstellar object would arrive at Mars within the same 3-month window that NASA announces the strongest biosignature candidate in Martian exploration history? Not just arrive somewhere in the solar system, specifically arrive near Mars, specifically during this particular moment in human scientific discovery. Start with interstellar object frequency. Based on our 3 confirmed detections and estimated detection efficiency, astronomers calculate that roughly 5 to 10 interstellar objects pass through the inner solar system inside Jupiter's orbit per year. Most are too faint or moving too fast for our current telescopes to spot, but they're there, zipping through our neighborhood at hyperbolic velocities, completely indifferent to our existence. Now consider Mars's position. Mars orbits the Sun at an average distance of 1.52 astronomical units, taking 687 Earth days to complete one orbit. At any given moment, Mars occupies a specific point in 3-dimensional space. For an interstellar object to pass within what we'd call close proximity, say, 30 million kilometers, which is where 3 I/Atlas's trajectory takes it, requires the object's path to intersect a relatively small volume of space at precisely the right time. The solar system is big, absurdly big. The region inside Jupiter's orbit represents a volume of approximately 900 million cubic astronomical units. Mars, even accounting for its orbital motion, occupies a tiny fraction of that space. Calculating the probability that any random interstellar object would pass within 30 million kilometers of Mars is essentially asking what percentage of solar system space does Mars's gravitational neighborhood occupy? The answer is roughly 0.0001%, 1/10,000th of 1%. If interstellar objects are randomly distributed in their trajectories, which current models assume they are, then any single interstellar visitor has a 0.0001% chance of passing close to Mars. Put another way, you'd expect one Mars-proximate interstellar object for every million interstellar objects entering the inner solar system, at a rate of 5 to 10 objects per year. That means you'd expect one Mars encounter every 100,000 to 200,000 years. We've been capable of detecting interstellar objects for approximately 8 years. The statistical expectation was that we wouldn't see a single Mars-proximate interstellar visitor in our lifetimes, our children's lifetimes, or possibly our species' entire technological civilization. Yet here we are. Now let's layer on the biosignature timing. Perseverance has been operating on Mars since February 2021. It collected the Chayava Falls sample on July 21st, 2024. NASA announced the leopard spot biosignatures publicly in early September 2025. The window of discovery spans roughly 14 months from sample collection to public announcement. 3I/Atlas was discovered on July 1st, 2025. Its Mars closest approach occurs in mid-November 2025. The window of Mars encounter spans approximately 4.5 months from discovery to closest approach. These two windows, biosignature discovery and interstellar visitor arrival, overlap almost perfectly. Both events are happening in the same human calendar year, a time period that represents 0.00000004% of Mars's geological history. Let me put that in perspective. You can feel Mars has existed for 5 billion years. If we compress that entire timeline into a single 24-hour day, with Mars forming at midnight and now being 11:59 p.m., then the overlap between biosignature discovery and 3I/Atlas arrival occurs in the final 0.0008 seconds of that day. Less than a millisecond. A cosmic eye blink. Dr. Gregory Laughlin, an astronomer at Yale who specializes in orbital dynamics, calculated something similar for the Oumuamua encounter in 2017. He noted that the odds of Oumuamua passing through the inner solar system during humanity's narrow window of technological capability after we developed telescopes powerful enough to detect it, but before we might colonize the solar system and lose interest in random interstellar debris, was statistically curious. His exact words, "The timing makes you wonder whether the universe is trying to get our attention." He was joking. Probably. Scientists maintain plausible deniability about these things. But let's continue stacking probabilities. Not just that an interstellar object approaches Mars. Not just that it happens during a biosignature discovery year. But that this particular interstellar object carries an 8:1 CO 2-to-water ratio, the exact chemistry Mars would benefit from for atmospheric enhancement. Of the 3 confirmed interstellar objects, one is chemically anomalous with no outgassing, Oumuamua, one is boringly normal with water-dominated chemistry, Borisov, and one is CO2-dominated 3I/Atlas. What percentage of interstellar comets should be CO2-dominated? We don't know. Our sample size is literally 2 comets Borisov and 3I/Atlas. That's not enough data to establish distributions, but based on solar system comets, CO2-dominated objects are rare. Perhaps 5% of comets show CO2 to water ratios above 2:1. Ratios above 5:1 are almost unheard of. 3I/Atlas's 8:1 ratio would place it in perhaps the top 1% of unusual comets, if solar system chemistry is any guide to interstellar chemistry. So now we're calculating what are the odds that a top 1% unusual interstellar comet passes within 0.0001% of Mars's orbital space during a 0.00000004% window of Martian geological time that coincides with human biosignature discovery. Multiply those probabilities together, 0.01x, 0.000001x, 0.00004 equal sign 0.0000000000004 or 4 quadrillionths. That's a 1 in 250 trillion chance. To put that in perspective, you're more likely to win the Powerball lottery 5 times consecutively than to see this particular confluence of events occur randomly. Now, here's where responsible science requires me to pump the brakes on that calculation, because those numbers are misleading. We're cherry-picking parameters. We're defining the significance windows after observing the events, which creates selection bias. We're assuming independence between events that might not actually be independent. We're using uncertainty ranges in our favour to make the coincidence seem more extreme. If you pick any random astronomical event and look hard enough, you'll find coincidental timing with something else interesting. The Chelyabinsk meteor exploded over Russia on February 15th. 2013, the same day asteroid 2012 DA14 made a close approach to Earth. Coincidence? Yes, actually, just coincidence. People wanted to connect them, but they were completely unrelated events with entirely different orbital origins. The difference here is that we're not connecting random unrelated events. We're connecting events involving the same planet, similar chemistry, and overlapping time frames. The pattern isn't arbitrary, it's specific. Still, 250 trillion is an absurd number, and you should be skeptical of it. I'm skeptical of it. But even if we're off by a factor of 1000, even if the real probability is 1 in 250 billion instead of 1 in 250 trillion, we're still talking about something that shouldn't happen within observable human history. And yet it's happening right now. While you're listening to this, 3I/Atlas is closing distance on Mars, invisible to Earth-based telescopes, carrying its payload of carbon dioxide on a trajectory that was set 300,000 years before Perseverance drilled into Chayava Falls and found leopard spots that might represent ancient Martian biology. Here's what keeps me staring at spreadsheets at midnight. Either this is the most spectacular coincidence in astronomical observation history, or there's something about the relationship between interstellar objects, planetary chemistry, and biosignatures that our current scientific models fundamentally don't understand. Both possibilities are terrifying in their own way. One suggests the universe is far more random than our pattern-seeking brains want to believe. The other suggests the universe is far more organised than our materialist physics currently explains. The data doesn't care which interpretation makes us comfortable. The data just sits there, waiting for interpretation, while Mars and 3I/Atlas continue their invisible rendezvous in a cosmic darkness we're only now beginning to illuminate. Retry F. Imagine Mars 3.8 billion years ago. Not the frozen rust-coloured desert we see today, but a world with rivers carving deltas, lakes reflecting a thicker atmosphere, and volcanic vents pumping heat and chemistry into underwater environments. Now imagine that world dying. Not suddenly, not dramatically, but slowly over hundreds of millions of years as its magnetic field collapsed, its atmosphere bled into space, and its surface water evaporated or froze into subsurface ice. Everything that made Mars habitable simply stopped. This is planetary death, and it's more common in the universe than planetary life. Most rocky planets probably look like Mars, eventually cold, dry, atmospherically anemic corpses orbiting their stars in silent testimony to what could have been. But here's the question nobody's quite figured out how to answer. Can a dead planet wake up? Not through human intervention. We've already established that Terraforming requires resources we won't have for centuries. I'm talking about natural resurrection, cosmic defibrillation, the universe delivering exactly what a dormant world needs to restart the chemical processes that once made it habitable. Even temporarily, even partially, let's break down what Mars actually needs. First, atmospheric pressure. We've covered this already. Current pressure is 600 pascals. Needs to be at least 6000 pascals for stable liquid water. That requires adding massive amounts of gas, preferably greenhouse gases that can trap heat. Carbon dioxide tops the list because Mars already has the infrastructure to process it. The chemistry is familiar. The planet remembers how to work with CO2. Second temperature increase. Mars's average surface temperature of -63 Celsius needs to climb to at least -20 Celsius globally for subsurface ice to begin melting during summer months. That's a 43-degree increase, achievable only through enhanced greenhouse warming. More atmosphere means more heat retention, means higher temperatures, means more ice melting, means more water vapor in the atmosphere, means even more greenhouse warming. It's a positive feedback loop, the kind that can cascade once you push past a threshold. Third, liquid water. Even briefly, this is the game changer. Liquid water acts as a solvent, enabling chemical reactions that can't occur in ice or vapor. It mobilizes nutrients, transports dissolved gases, facilitates mineral formation, and creates environments where complex chemistry, maybe even biology, can temporarily operate. You don't need oceans. You don't even need lakes. Just intermittent liquid water films in soil. Lasting hours or days during peak temperatures would be revolutionary. Fourth, protection from radiation. Mars lacks a global magnetic field, so its surface gets hammered by cosmic rays and solar radiation that would sterilize most biological processes. But you don't need a magnetic field if you have atmosphere. A thicker atmosphere absorbs and scatters radiation, creating safer conditions near the surface. Every additional pascal of pressure helps. Now here's what makes the 3I/Atlas scenario genuinely interesting from a planetary science perspective. It potentially delivers 3 of these 4 requirements simultaneously. The CO2 provides both atmospheric pressure increase and greenhouse warming capability. The greenhouse warming raises temperatures. Higher temperatures sublime more of Mars's existing ice caps, adding water vapor to the atmosphere and creating conditions for temporary liquid water. 3 birds with 1 cosmic stone. The only thing 3I/Atlas can't provide is radiation protection, but that's a secondary concern if we're only talking about temporary chemical activity rather than sustained biology. Even Earth's early atmosphere, before the oxygenation event too, 4 billion years ago, offered minimal radiation protection. Life adapted by hiding in oceans, living in soil, and developing repair mechanisms for radiation damage. Mars's subsurface chemistry could theoretically handle brief radiation exposure if everything else suddenly became favourable. Dr. Robert Zubrin, an aerospace engineer who's spent decades analysing Mars' habitability, proposed something called the Mars Oasis hypothesis back in the 1990s. His idea Mars doesn't need global terraforming to support biological activity. It just needs localized oases, small regions where temporary conditions allow liquid water and active chemistry. These oases could appear naturally during favorable orbital cycles when Mars's axial tilt increases solar heating, or they could be triggered by external events like comet impacts or volcanic activity. The math on comet impacts is actually well established because we've witnessed several. When comet Shoemaker-Levy 9 impacted Jupiter in July 1994, astronomers calculated that the energy released approximately 6 million megatons of TNT across multiple fragments would have been sufficient to vaporize trillions of tons of ice if Jupiter had surface ice to vaporize. Jupiter didn't, being a gas giant. But the principle applies to rocky planets. Mars has been hit by comets before. We know this from impact craters showing specific characteristics: high volatile content, unusual ejecta patterns, evidence of water interaction during impact. The most famous example is probably the crater cluster in the Elysium Planitia region, where impacts around 5 million years ago might have created temporary lakes that lasted for decades or centuries before freezing and sublimating away. But those were direct impacts, violent, destructive events that crater the surface and temporarily melt ice through brute force kinetic energy. A close flyby is different, gentler. Instead of explosive vaporization, you get slow atmospheric delivery through outgassing. The comet's nucleus doesn't need to hit Mars. It just needs to pass close enough that Mars's gravity captures some of the sublimating gases. How close is close enough? That depends on Mars's gravitational influence and the comet's outgassing rate. Mars's Hill sphere, the region where its gravity dominates over the Sun's, extends about 0.98 million kilometers from the planet. Within this zone, Mars can theoretically capture gas molecules from a comet's coma if the relative velocities and densities are favourable. 3 I/ATLAS's closest approach of 30 million kilometers is far outside this capture zone, which means direct atmospheric transfer is essentially impossible. So we're not talking about 3 I/ATLAS donating its CO2 directly to Mars. The distances don't work, but here's what does work: ionospheric interaction. When a comet passes through interplanetary space near a planet with an ionosphere, Mars has a weak one. The comet's coma interacts with the planet's upper atmosphere through electromagnetic effects. Charged particles from the solar wind, deflected by the comet's magnetic field, can be redirected toward the planet, causing temporary ionospheric disturbances. These disturbances alter how the upper atmosphere behaves. They can increase atmospheric escape rates bad for Mars, or they can temporarily enhance atmospheric density at high altitudes, potentially good for Mars if it changes how solar radiation interacts with atmospheric chemistry. Dr. Gwen Hanley at NASA Goddard published research in 2023 showing that unexpected ionospheric disturbances on Mars during certain orbital periods correlated with measurable surface pressure changes detected by the InSight lander before it went offline. The mechanism isn't fully understood, but the correlation exists. Something about upper atmospheric electromagnetic interactions can influence surface conditions. If 3 I/ATLAS's passage creates similar ionospheric disturbances, and given its unusual chemistry, it might create unusual electromagnetic signatures. We could see measurable effects on Mars's surface environment during and shortly after closest approach. What would those effects look like? Probably subtle. A temporary pressure spike of 10 to 20 pascals, barely detectable. Temperature increases of 2 to 5 degrees Celsius in equatorial regions, most noticeable during local summer. Enhanced sublimation of seasonal frost deposits, creating brief water vapor abundance increases in the lower atmosphere. Nothing dramatic. Nothing that would show up in casual orbital photography. But to instruments specifically monitoring atmospheric chemistry like the Mars atmosphere and volatile evolution. MAVEN's spacecraft that's been orbiting Mars since 2014, these changes would be measurable. MAVEN's mass spectrometer can detect atmospheric composition changes down to parts per billion. Its ultraviolet spectrograph tracks how gases escape into space in real time. If 3 I/ATLAS's passage triggers anything unusual, MAVEN will record it. And here's the truly interesting part: MAVEN's data is publicly available through NASA's Planetary data system, usually with a 6-month delay for validation and calibration. The November 2025 encounter data will be available around May 2026. Anyone with the right software and patience can download it, analyze it, and look for anomalies. We'll know. Not immediately. Not while 3I/Atlas is making its closest approach behind the sun where nobody can watch. But eventually, in 6 months or a year, when the data comes out and researchers start digging through atmospheric measurements, we'll know whether this cosmic coincidence had any measurable effect on Mars's environment. Until then, we're left with a planet that's been dormant for billions of years and an interstellar visitor carrying the chemistry that dormant planet once used to stay warm. They're meeting in darkness, invisible to human observation, following gravitational mechanics that were determined when dinosaurs were still 300,000 years in Earth's future. Either nothing will happen, and this entire story becomes a footnote about how humans love finding patterns in cosmic randomness, or something will happen, something subtle, something temporary, something that makes us reconsider what planetary death actually means and whether the universe occasionally provides the resuscitation equipment dead worlds need to remember they were once alive. Let's zoom out for a moment. Way out. Because if we're going to understand why 3 interstellar visitors in 8 years might be significant, we need to think about how star systems interact across the vast emptiness of the galaxy. And that requires talking about something called the Galactic Habitable Zone, a concept that sounds like science fiction but is actually serious astrophysics. Our solar system sits approximately 26,000 light-years from the galactic centre, in what astronomers call the Orion Arm, a minor spiral arm between 2 major ones. This location isn't random luck, it's actually prime real estate in galactic terms, close enough to the centre that heavy elements carbon, oxygen, iron, all the building blocks of rocky planets are abundant. But far enough out that supernova explosions and gamma-ray bursts don't sterilize planets every few million years. The Goldilocks zone, galactic addition, most star systems in this region are roughly 4 to 5 light-years apart. Alpha Centauri, our nearest neighbour, is 4.37 light-years away. Barnard's star sits 5.96 light-years distant. These distances feel enormous, and light takes years to cross them, but comets don't care about light speed. They move at tens of kilometres per second, drifting through the gravitational boundaries between stars on journeys lasting millions of years. Here's what makes this relevant. Every star system has an Oort cloud, a spherical shell of icy bodies extending roughly 1 light-year from the parent star. These clouds are gravitational borderlands, places where the star's influence fades and galactic dynamics take over. When stars pass relatively close to each other within a light-year or so, their Oort clouds overlap. Gravitational perturbations knock comets loose. Some fall inward toward their parent star. Others get ejected entirely, flung into interstellar space on one-way trips to nowhere in particular. Dr. Amaya Morrow-Martin, an astrophysicist at the Space Telescope Science Institute, calculated in a 2019 study that each star system probably ejects billions of comets over its lifetime. Billions. Most are small kilometre-sized or smaller, but collectively they represent an enormous mass of water ice, carbon dioxide, organic molecules and other volatiles drifting between the stars. The galaxy is filled with this material, an invisible ocean of frozen chemistry flowing through the darkness. Now consider the implications. If every star system is constantly ejecting comets, and if those comets travel through interstellar space for millions of years before potentially encountering other star systems, then planetary systems are continuously exchanging material. Not intentionally, not through any intelligence or design, just through gravitational mechanics playing out over geological timescales. This process has a name, Lithopanspermia, when it involves rock fragments that might carry microorganisms, or molecular panspermia, when it involves organic chemistry and volatile compounds. The idea dates back to the 1970s, when scientists like Fred Hoyle and Chandra Wickramasinghe proposed that life might spread between planets via comets. The hypothesis was controversial then and remains speculative now, but the underlying mechanics are solid. Comets do travel between stars. They do carry complex chemistry. They do occasionally impact planets or pass close enough to interact with planetary atmospheres. What if this isn't random distribution? What if certain regions of the galaxy, certain stellar neighborhoods, share chemistry more efficiently than others? We know that star systems born from the same molecular cloud siblings essentially tend to have similar elemental compositions. But what about chemistry mixing over longer timescales through comet exchange? There's preliminary evidence this might actually happen. A 2021 paper in the Astrophysical Journal analysed the chemical composition of long-period comets entering our inner solar system from the Oort cloud. The researchers found subtle variations, suggesting some comets formed in slightly different chemical environments than others. Despite all originating from the same molecular cloud that birthed our solar system, the hypothesis these comets might have been captured from passing stars early in our solar system's history, when stellar encounters were more frequent. If our solar system captured comets from other stars 4 billion years ago, then presumably those other stars also captured some of our comets. There's been an exchange, a mixing, and if Mars once had life, if those leopard spots in Jezero crater really do represent ancient biology, then Earth and Mars shared a habitable period when both planets had liquid water and thick atmospheres. Impacts between Mars and Earth were common during the late heavy bombardment period, around 3.9 billion years ago. Rocks ejected from Mars by impacts eventually landed on Earth, and vice versa. We've found Martian meteorites in Antarctica. We know the transport pathway exists. So here's the scenario that makes my brain itch. What if early Mars developed biology independently, or received it from Earth through meteorite exchange, or got seeded by an interstellar comet from another star system entirely? And what if, after Mars's magnetic field collapsed and its atmosphere escaped, the planet's biological experiment went dormant, but the chemistry remained, frozen in subsurface ice, waiting. Now, scale up. Our stellar neighbourhood contains hundreds of stars within 20 light-years. Many have planetary systems we've detected, exoplanets around nearly every star we've examined closely enough. Some of those planets are rocky. Some orbit in their star's habitable zone. And all of them, presumably, are exchanging comets through the same gravitational mechanisms that give us Oumuamua, Borisov, and 3I/Atlas, Dr. Edward Bell-Bruno, a mathematician specialising in celestial mechanics, proposed something fascinating in 2012 called weak transfer orbits. These are gravitational pathways through the solar system that require minimal energy but take enormous amounts of time. A comet following a weak transfer orbit might drift for millions of years, gradually spiralling inward, until it eventually encounters a planet, not through targeted trajectory, but through patient gravitational choreography playing out across geological epochs. What if interstellar comets use similar weak transfer dynamics at galactic scales? What if there are gravitational rivers flowing through stellar neighbourhoods? Channels that naturally funnel ejected comets towards certain types of planetary systems we wouldn't know. We've only been detecting interstellar objects for 8 years. That's not enough time to map galactic traffic patterns that operate on million-year timescales. But we can look for clues: 3 interstellar visitors, 3 different chemistries, Oumuamua from who knows where, possibly a nitrogen iceberg from a Pluto-like exoplanet based on one recent hypothesis, Borisov from a system with chemistry similar to ours, water-rich, conventional, 3I/Atlas from somewhere cold and CO2-rich, perhaps a star system with a different carbon-to-oxygen ratio than our own. Each visitor tells us something about where it came from. Each chemistry is a fingerprint of its birth environment. And collectively, they're starting to paint a picture of chemical diversity in our stellar neighbourhood. We're sampling the galaxy's ice cream flavours, if you will, one cosmic delivery at a time. The pattern, if there is a pattern, won't become clear until we've detected dozens or hundreds of interstellar objects. But imagine if, 20 years from now, we've catalogued 100 interstellar visitors, and we start noticing that CO2-rich comets tend to approach Mars more frequently than water-rich comets do. Or that planets with certain atmospheric compositions seem to attract certain types of interstellar chemistry. It would suggest that planetary systems and interstellar object distributions aren't independent, that there's coupling, correlation, maybe even causation we don't yet understand. This is where science fiction and science fact start getting uncomfortable together. Because if interstellar comets naturally deliver atmospheric components to planets that have lost their atmospheres, and if that delivery happens preferentially to planets with certain characteristics like ancient lake beds and subsurface ice and potential biosignatures, then we're describing a universe that behaves almost as if it's trying to keep potentially habitable planets alive. Not through intelligence. Not through design in any anthropomorphic sense, but through physics and chemistry operating at scales we're only beginning to measure. Creating feedback loops between stellar neighbourhoods and planetary environments that might naturally favour life's persistence across geological timescales. Or maybe it's all coincidence. Maybe 3I/Atlas just happens to be CO2 rich. Just happens to be approaching Mars. Just happens to arrive during the same year we discovered biosignature candidates. Maybe the universe is exactly as random as our textbooks claim, and humans are just exceptionally good at finding meaning in meaningless patterns. The difference between these possibilities isn't philosophical, it's observational. And we're about to collect the data that might tell us which interpretation fits reality better. Maven is watching. Perseverance is drilling. JWST is imaging. The asteroid warning networks are scanning. And somewhere in the darkness behind the sun, an interstellar visitor continues its ancient journey, completely unaware that the tiny creatures on the third rock from one particular star have noticed its arrival and are wondering what it all means. Here's something nobody's really talking about yet, but it's going to become the conversation within the next 6 months. We're about to conduct the most comprehensive observational study of an interstellar object in human history, and we didn't even plan it. The timing, the technology, and the scientific interest have aligned in a way that makes 3I/Atlas potentially the most scrutinized comet ever observed. Let me walk you through what's actually going to happen and why you should care. Right now, as 3I/Atlas makes its closest approach to Mars in mid-November 2025, it's invisible to Earth-based telescopes because of solar conjunction. But that invisibility is temporary. By late December 2025, the geometry changes. The comet emerges from behind the Sun, moving into observable positions for both ground-based and space-based instruments. And that's when the real science begins. The James Webb Space Telescope has already observed 3I/Atlas once. Back in July, shortly after discovery, those initial observations gave us the CO2 to water ratio and the green glow signatures. But JWST's observation schedule is booked months in advance by competing research teams from around the world. Getting telescope time requires submitting detailed proposals, peer review, and approval from NASA's allocation committees. It's harder than getting concert tickets for Taylor Swift, except when something becomes scientifically urgent. When Oumuamua was discovered in 2017, observatories worldwide scrambled to get eyes on it before it disappeared forever. Research schedules got rearranged. Director's discretionary time emergency telescope access reserved for unexpected discoveries got activated. The astronomical community moves fast when necessary, and 3I/Atlas is triggering that same response now. Dr. Stephanie Millam, Deputy Project Scientist for Planetary Science at JWST, mentioned in an October 2025 conference presentation that additional observation windows for 3I/Atlas have been approved for January and March 2026. The January observations will capture the comet post-perihelion after its closest approach to the Sun when outgassing should be at peak intensity. The March observations will track how the chemistry changes as the comet moves back toward interstellar space and solar heating decreases. What are they looking for? Specifically chemical evolution. Comets don't maintain constant composition as they approach and leave the Sun. Different ices sublimate at different temperatures, creating a predictable sequence of chemical signatures. Water ice starts outgassing around 3 AU, carbon dioxide becomes prominent at 5 AU, carbon monoxide, even farther out, by watching how 3I/Atlas's spectrum changes over several months. Astronomers can build a complete chemical profile, not just what's on the surface, but what's buried deeper in the nucleus. And here's the kicker: if 3I/Atlas shows any anomalies, unexpected chemicals, unusual outgassing patterns, anything that doesn't fit standard comet models, those anomalies will be documented with unprecedented precision. JWST's spectroscopic resolution is so high it can detect molecular signatures that were invisible to previous telescopes. We're not just watching a comet, we're conducting a forensic analysis of interstellar chemistry at a level that wasn't possible even 5 years ago. Meanwhile, Mars-side observations are equally important. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, will be watching the upper atmosphere during 3I/Atlas's November approach. MAVEN's instruments measure atmospheric escape rates, ionospheric density, solar wind interactions, basically everything happening in Mars's thin upper atmosphere where space and planet meet. If 3I/Atlas's passage causes any electromagnetic disturbances or temporary atmospheric changes, MAVEN will record them. The data won't be available immediately. NASA's standard protocol requires 6 months of validation and calibration before releasing raw data to the public. So we're looking at May or June 2026 before researchers can start digging through the November 2025 observations. But when that data drops, it'll be analysed by dozens of research teams worldwide, each looking for different signatures, different anomalies, different clues about what happened during the invisible encounter. Ground-based observations add another layer. The European Southern Observatory's Very Large Telescope in Chile, 4 8.2-metre telescopes operating together, has the angular resolution to potentially image 3I/Atlas's nucleus directly once it emerges from solar conjunction. Not just a point of light, but actual surface features if the comet is large enough and close enough. For comparison, they managed to image the nucleus of 2I/Borisov in 2019, revealing an elongated shape and active outgassing jets. If they can do the same for 3I/Atlas, we'll know whether this interstellar visitor has any structural weirdness like Oumuamua's elongated geometry. Radio telescopes are also getting involved. The Atacama Large Millimeter Array in Chile, ALMA, specializes in detecting molecular signatures through radio wavelengths. ALMA can identify specific molecules that optical telescopes miss: hydrogen cyanide, methanol, formaldehyde, all the organic chemistry that might be hiding in 3I/Atlas's coma. A 2020 ALMA observation of 2I/Borisov detected carbon monoxide concentrations that helped pinpoint where, in another star system, that comet likely formed. The same technique will be applied to 3I/Atlas. And then there's citizen science. Amateur astronomers with backyard telescopes have become increasingly important to professional astronomy. When Oumuamua was discovered, hundreds of amateur observers contributed light curve data measurements of how the object's brightness changed over time that helped professionals calculate its rotation rate and shape. For 3I/Atlas, the amateur community is already mobilised. Online forums are coordinating observation schedules. People are sharing telescope time. Someone in Australia observes during their night, uploads the data, and someone in Chile continues tracking during their night. It's a global relay race with the comet as the baton. What could these observations reveal? Best case scenario. Everything behaves exactly as predicted. The comet's chemistry matches theoretical models. No anomalies appear in Mars's atmosphere. The trajectory follows Newtonian mechanics perfectly. We confirm that 3I/Atlas is exactly what it appears to be, a natural comet with unusual but explicable chemistry, passing through our solar system on a one-way trip that happens to bring it near Mars through pure gravitational coincidence. That would be scientifically satisfying and reassuring. Worst case scenario, or most interesting case. Depending on your perspective, we find anomalies we can't explain. Maybe MAVEN detects atmospheric disturbances on Mars that don't match any known ionospheric models. Maybe JWST discovers molecular signatures in 3I/Atlas's coma that shouldn't exist in natural comets. Maybe the trajectory shows tiny deviations from predicted paths, suggesting non-gravitational forces we don't understand. Any of these discoveries would be simultaneously exciting and troubling, opening questions faster than we could answer them. The middle scenario is most likely we get better data, refine our models, and end up with more sophisticated questions than we started with. Science rarely delivers clean answers. It delivers better questions, which lead to better experiments, which lead to even better questions. That's how knowledge actually grows, not through sudden revelations, but through incremental refinement of understanding. But here's why the next 6 months matter so much. This is the window. 3I/Atlas is moving at 32 kilometers per second relative to the Sun. By mid-2026, it'll be beyond Mars's orbit, heading outward toward interstellar space. By 2027, it'll be too faint for most telescopes to detect. By 2028, it'll be gone. Another interstellar visitor disappearing into the cosmic darkness from which it emerged. We get one chance to study it properly, one opportunity to collect data that might not come again in our lifetimes. Think about Oumuamua. We had maybe 2 weeks of decent observation time before it faded from view. Astronomers are still arguing about what it was because we didn't get enough data. The observational window closed before anyone realized how important those observations would become. We missed things, important things, and now we'll never know for certain whether Oumuamua was an unusual comet, a nitrogen iceberg, or something else entirely. We're not making that mistake with 3I/Atlas. The observation schedule is aggressive. Multiple telescopes, multiple wavelengths, multiple research teams all coordinating to extract maximum information before the opportunity disappears. And the Mars component adds urgency that Oumuamua and Borisov didn't have. This isn't just about characterizing an interstellar visitor. It's about understanding whether that visitor had any effect on a planet that might have once harbored life. So when I say the next 6 months are critical, I mean it literally. Between now and June 2026, we'll collect data that either confirms 3I/Atlas as an interesting but ultimately normal interstellar comet, or reveals something that challenges our understanding of how chemistry, biology, and cosmic mechanics interact across interstellar distances. Either outcome is significant. Both outcomes will be published in papers you can read yourself if you're curious enough to dig through NASA's archives and astronomical journals. The universe is conducting an experiment above our heads right now, and for once, Humanity has the tools to measure the results. The question is whether we'll recognize significance when we see it, or whether we'll be so invested in comfortable explanations that we miss something genuinely extraordinary hiding in plain sight within the data. Retry F. So here's the part where I'm supposed to tell you what all this means, where the narrator delivers the satisfying conclusion, ties up the loose ends, and sends you off to sleep with answers instead of questions. But that's not the story we're living through right now, because the truth is, we're standing at one of these rare moments in science where the data hasn't caught up to the mystery yet. And nobody, not NASA, not Harvard astronomers, not even the people writing the observation schedules, actually knows what we're going to find. Let me be uncomfortably honest with you about something the scientific community doesn't love admitting publicly. We're really good at detecting patterns, but we're terrible at knowing which patterns matter. Human brains evolved to find significance in coincidence because that behaviour kept our ancestors alive. The rustling in the grass might be wind, or it might be a predator. Our ancestors who assumed predator and ran away survived more often than the ones who assumed wind and stayed put. Natural selection hardwired us to see threats and meaning everywhere. Even when randomness provides perfectly adequate explanations, this cognitive bias called apophenia, the tendency to perceive meaningful connections between unrelated things, haunts astronomy constantly. People see faces on Mars in random rock formations. They find alien megastructures in star brightness variations that turn out to be dust clouds. They connect dots between events separated by millions of light years and billions of years, constructing narratives that feel compelling but collapse under mathematical scrutiny. So when I tell you that 3I/Atlas's timing feels significant, you should immediately ask, is this actual significance? Or is this apophenia wearing a lab coat? That's not skepticism. That's responsible thinking. And honestly, I don't know the answer yet. Nobody does. We won't know until the data comes in, gets analysed, gets peer-reviewed, and either survives criticism or gets demolished by it. But here's what we do know right now, today. Without speculation, the universe operates on physical laws that don't care about human narrative preferences. Gravity follows equations, chemistry follows thermodynamics. Objects move through space according to momentum and gravitational fields, not according to dramatic timing that makes good stories. If 3I/Atlas and the Martian biosignature discovery are genuinely connected through something other than coincidence, that connection must operate through physics we can measure, chemistry we can detect, or mechanisms we can eventually understand. Which means there are really only 3 possible explanations for what we're witnessing. Let's walk through them honestly, including the uncomfortable implications of each. Option 1. Pure coincidence. 3I/Atlas is just a comet following gravitational mechanics on trajectory, set 300,000 years ago, when Neanderthals still lived in European caves. Its chemistry is unusual but natural. Formed in the cold outer regions of some distant star system we'll probably never identify. Its path brings it near Mars through the same blind probability that occasionally causes lightning to strike the same place twice. The biosignature discovery at Jezero crater is independent. Perseverance was going to find those leopard spots regardless of whether any interstellar visitor happened to be nearby. The timing is remarkable but meaningless. The universe's equivalent of a statistical hiccup. This explanation requires no new physics, no conspiracy theories, no exotic mechanisms. It's the most parsimonious option, Occam's razor in action. It also requires accepting that a 1 in 250 trillion probability event just happened during our lifetime, which feels psychologically unsatisfying, even though improbable events must occur somewhere, sometime. Somebody wins every lottery, even though each individual's odds are essentially zero. Option 2. Natural coupling we don't yet understand. Maybe planetary systems with certain characteristics, ancient water systems, subsurface ice deposits, dormant but potentially active chemistry interact with interstellar object trajectories in ways our current models don't account for. Perhaps planets with significant magnetic anomalies, like Mars's crustal magnetic fields, create electromagnetic signatures that interact with the charged particles surrounding interstellar comets, subtly influencing trajectories over millions of years. Or maybe galactic dynamics preferentially funnel certain types of interstellar objects towards certain types of planetary environments through weak gravitational focusing we haven't detected yet. This explanation requires new physics or at least significant revisions to our understanding of how planets and interstellar objects interact. It's more speculative than option 1, but doesn't invoke anything supernatural or intelligent. It suggests the universe is more interconnected than we currently model, with feedback loops operating across interstellar distances and geological timescales. If true, it would revolutionize planetary science and galactic dynamics. It would also be extraordinarily difficult to prove without decades of additional observations. Option 3, designed intervention. Something intelligence. Technology. Processes we have no framework for understanding is deliberately delivering atmospheric components to Mars. Maybe von Neumann probes launched by extinct civilizations millions of years ago. Self-replicating machines that continue executing terraforming protocols long after their creators disappeared. Maybe the galaxy itself has developed emergent properties through billions of years of planetary system interactions, creating something that functions like intelligence without being conscious in any way we'd recognize. Maybe we're completely wrong about what consciousness and intention even mean at cosmic scales. This is the explanation that makes scientists deeply uncomfortable. Not because it's impossible, the universe is under no obligation to make sense to evolved primates on one planet, but because it's unfalsifiable with current data. You can't disprove invisible superintelligences or galaxy-spanning mechanisms that operate on timescales beyond human comprehension. It's the aliens did it explanation that ends investigation rather than promoting it. Science advances by asking questions that experiments can answer. Did ancient aliens set this up? Isn't a scientifically useful question unless you can design an observation that would distinguish between yes and no. So where does that leave us suspended between possibilities, waiting for data that might not arrive for months or years? But that suspension isn't comfortable uncertainty, it's productive uncertainty. It's the state where science happens. The period between observation and explanation is where human knowledge actually grows, where we're forced to confront how much we don't know and develop better tools for finding out. Here's what I find genuinely fascinating, regardless of which explanation turns out to be correct. We're living through a moment that future historians of science will study. If it's pure coincidence, they'll analyze it as a case study in human pattern recognition and the psychology of significance. If it's natural coupling, they'll mark it as the beginning of a new understanding of planetary interstellar interactions. If it's something else entirely, well, that would be the most interesting timeline of all. But the outcome depends entirely on what we do next. Do we watch carefully? Do we collect data rigorously? Do we analyze results honestly, even when they contradict our preferred narratives? Do we resist the temptation to reach premature conclusions just because uncertainty feels uncomfortable? The universe is indifferent to our preferences, but it's not indifferent to our attention. Nature rewards careful observation with discovery. The scientists tracking 3I/Atlas right now, the engineers monitoring MAVEN's atmospheric sensors, the researchers who'll spend 2026 analysing spectra and calculating trajectories. They're doing the unglamorous work that occasionally produces breakthrough insights. And you're part of this moment too. You're paying attention, you're asking questions. You're not satisfied with easy answers or comfortable dismissals. That curiosity, that refusal to accept is probably nothing without actually checking, is what drives human understanding forward. It's what got us from bronze tools to space telescopes in a few thousand years. It's what might eventually answer whether we're alone in a random universe or part of something larger and stranger than our current frameworks can comprehend. The data is coming. JWST observations in January and March 2026. MAVEN atmospheric measurements releasing in mid-2026. Ground-based tracking continuing through 2027. The Chiava Falls sample analysis ongoing at Perseverance's mobile laboratory, with more drilling planned for 2026 if the rover's systems remain operational. We don't know what those data will show yet, but we're about to find out. And that anticipation, that gap between question and answer, is where the most honest science lives. Not in certainty, not in dogmatic adherence to preferred explanations, but in careful observation of a universe that keeps surprising us with complexities we didn't anticipate and patterns we don't yet understand. So stay curious, stay skeptical, and keep watching the skies, because the universe is conducting an experiment whether we're paying attention or not. Let me tell you about a photograph that doesn't exist yet. Sometime in late 2026 or early 2027, when the Mars sample return mission architecture finally gets sorted out, assuming Congress continues funding it, assuming international partnerships hold together, assuming the engineering challenges get solved, a rover will collect rocks from Jezero crater. Those rocks will be sealed in containers, launched into Martian orbit, captured by a return spacecraft, and eventually delivered to Earth. And when those samples arrive, probably sometime in the early 2030s, scientists in biosafety level 4 laboratories will photograph them with electron microscopes capable of resolving individual organic molecules. One of those photographs might show definitive evidence of ancient Martian biology, or it might show compelling geology that mimics biology. Either way, that photograph will exist in the same historical timeline as the observations we're making right now of 3I/Atlas. Future scientists will look at both pieces of evidence simultaneously, the ancient biosignatures and the interstellar visitors' timing, and they'll construct narratives about what it all meant. We're living through the beginning of a story whose ending hasn't been written yet. That's the uncomfortable truth about significant moments. You rarely recognize them while they're happening. The people watching Oumuamua zip through the inner solar system in 2017 didn't know they were observing humanity's first confirmed interstellar visitor until days after discovery, when the orbital calculations finally confirmed its hyperbolic trajectory. The astronomers taking spectra of 3I/Atlas in July 2025 didn't know they'd discovered the most CO2-rich interstellar object ever detected until the data analysis came back weeks later. Discovery happens in retrospect. Significance reveals itself slowly. So what is 3I/Atlas doing in Mars's orbit right this second? In mid-November 2025, while you're listening to these words, the comet is approximately 30 million kilometers from Mars, moving at 32 kilometers per second, outgassing carbon dioxide at rates we can't currently measure because it's hidden behind the Sun. Mars's MAVEN orbiter is recording atmospheric data. The Perseverance rover is continuing its geological investigation at Jezero crater. The James Webb Space Telescope is pointed elsewhere, observing distant galaxies, waiting for its scheduled observation window in January 2026. Nothing dramatic is happening. No explosions, no sudden atmospheric transformations, no alien motherships decloak from behind Jupiter. Just physics, chemistry, gravitational mechanics operating exactly as equations predict. An interstellar object following a trajectory determined before humans existed, passing near a planet that has been dormant longer than complex life has existed on Earth. And yet, here we are, paying attention, wondering, questioning whether the universe is trying to tell us something or whether we're just telling ourselves stories because that's what humans do. We're narrative machines, constructing meaning from events that might be meaningless. But let me propose something that might sound contradictory. Both interpretations can be true simultaneously. The universe can be operating through pure physical law, with no intention or design, and we can still extract genuine meaning from careful observation of those natural processes. Meaning doesn't require cosmic purpose, right? It requires understanding. And understanding comes from asking questions, even when you suspect the answers might be, it's just coincidence. Because here's what we've gained, regardless of whether 3I/Atlas's timing means anything cosmically significant. We've learned that interstellar objects arrive more frequently than we thought. We've discovered that their chemistry is far more diverse than models predicted. We've confirmed that our detection networks work well enough to spot these visitors early and track them accurately. We've demonstrated that international scientific cooperation can mobilize quickly when something interesting appears in the sky. We've shown that public interest in astronomy remains strong enough to support continued funding for observation programs. Those are all meaningful outcomes, even if 3I/Atlas turns out to be exactly what Occam's razor suggests. A natural comet with unusual chemistry passing through our solar system at a statistically improbable but ultimately random moment. Science progresses through accumulated observations, not just through breakthrough discoveries. Every data point matters. Every null result teaches us something. Every careful measurement refines our models slightly, and those incremental refinements accumulate into genuine understanding over time. The astronomer Carl Sagan used to say that extraordinary claims require extraordinary evidence. He was right, and that principle should guide how we interpret 3/Atlas's arrival. The claim that this is cosmic coincidence requires only ordinary evidence, the chemistry we've observed, the trajectory we've calculated, the timing we've documented. All of that fits within standard physical models. The claim that this represents something more natural coupling, designed intervention, universe-spanning patterns we don't understand requires extraordinary evidence we don't yet have. But Sagan also said something else that's equally important. Somewhere, something incredible is waiting to be known. That possibility, that openness to genuine discovery, even when it challenges our expectations, is what separates science from dogma. We should be skeptical of premature conclusions. We should demand rigorous evidence. But we should also remain intellectually prepared for the possibility that the universe is stranger and more intricate than our current models suggest. What does 3I/Atlas want with Mars? Nothing. Comets don't want anything. They're not conscious. They don't have intentions. They follow gravitational mechanics and thermodynamics, sublimating volatiles when solar radiation heats their surfaces, following trajectories determined by velocity and gravitational fields. Asking what a comet wants is a category error, like asking what the colour blue weighs or what silence tastes like. The question doesn't pass, but if we rephrase the question, what is happening between 3I/Atlas and Mars right now? And what might it tell us about how the universe operates? Then we're asking something scientifically meaningful. And the answer is we don't know yet. but we're measuring it as carefully as current technology allows, and we'll have better answers in 6 months, better still in 6 years, and genuinely comprehensive understanding in perhaps 6 decades, when we've detected enough interstellar objects to establish statistical patterns instead of arguing about individual cases. That's not a satisfying answer. It doesn't resolve uncertainty. It doesn't provide closure. But it's an honest answer. And honesty matters more than satisfaction when you are trying to understand reality instead of just constructing comfortable narratives about it. Here's my challenge to you: check back in 6 months. In May or June 2026, when MAVEN's atmospheric data from November 2025 becomes publicly available through NASA's Planetary data system, download it. You don't need a PhD to look at graphs of atmospheric composition over time. You don't need specialised software to see whether Mars's ionosphere showed unusual behaviour during 3 I/Atlas's closest approach. The data is public. The tools are free. You can verify this story's conclusion yourself instead of waiting for journalists or YouTubers to tell you what to think about it. And if you do that, if you actually look at the raw data, think critically about what it shows, and draw your own conclusions, then you're doing science. Real science. Not trusting authorities, not accepting comfortable explanations, but looking at evidence and reasoning carefully about what it means. That's what this moment asks of us. Not belief or disbelief, but curiosity disciplined by evidence. The universe doesn't care whether we understand it. Stars will continue fusing hydrogen into helium regardless of whether anyone's watching. Galaxies will continue rotating according to gravitational mechanics, whether or not conscious observers exist to measure them. Interstellar comets will pass through planetary systems, sometimes at statistically improbable moments. Whether or not anyone notices the timing, but we do notice. We do measure. We do wonder about patterns and meanings and connections that might exist beyond our current comprehension. That wondering, that refusal to accept ignorance as permanent, is what makes us human in the most profound sense. Not our tool use, not our language, but our stubborn insistence on asking questions even when the universe seems determined to answer only with more questions. 3 I/Atlas is out there right now, invisible behind the sun, completing its close approach to Mars. Whatever significance this moment has, cosmic or merely statistical, designed or random, meaningful or meaningless, won't be determined by what we believe about it. It'll be determined by what we observe, measure, analyse, and ultimately understand. The universe is waiting, not for our conclusions, but for our questions, not for our comfort, but for our curiosity. So stay curious. The story isn't finished yet. It's only just begun.